All right, so it's the second class for week two. And last week I was looking at the player controller more as like it's kind of a centerpiece of the game. And it allowed me to kind of talk about Visual Studio and C Sharp and like what all this stuff is going, what's this code looking like. Um, and I'll go through some more of the basics like properties and fields I was talking about last week. And I kind of talked about this awake method and how it's kind of going out and grabbing all this stuff. And that's really important. That's called initialization. And either you have to like connect everything up in the editor beforehand, or you kind of have to have your script go out and connect stuff. But the point is that a lot of objects are going to be talking to a lot of other objects, and objects communicate to each other by calling either like public methods or grabbing public properties. But it's like public parts of that class that when it becomes alive, it becomes an object. You're allowed to grab and read the public parts of it. So there's a lot of this communication with objects in programming. And I kind of was showing you how these properties were exposed out in the inspector and the Unity editor. That these are like public properties. And the cool thing is like you don't have to stay in the Visual Studio in the editor. You can like start tweaking stuff right in Unity. It's really good when you're working with designers and people who don't want to look at the code. In this stuff down here, which was all none, to start with, which would crash our game because we're going to like reference this stuff, and it's like I don't know what you're talking about. What object are you talking about? All that gets connected on that awake. So I was talking about events, awake, update, start, and start and awake are really like right at the beginning. It's like setting everything up, and then we go into these up. We just keep hitting that update loop over and over again until the game ends. And so this is where we're checking for user input. But I want to take a little break from coding because I kind of dived you in last class quite a bit. And let's look at this player game object, which it has a transform. Where in the world is it? And where it's its orientation and scale. And this player controller is a C# script which is available to us. All these components are C# scripts. It's just some of them are not available to us, and this one is in our assets in our project view. And the sprite render. So whenever you need to render something to the monitor, you're going to need a mesh render, a sprite render, or the base class is just render. If you go down here to add components, you can see a whole list of all the components. They're also up here. You can see them. And here's rendering. And here's the sprite render. And under mesh, there's mesh render for 3D. So let's take a little bit look at how this guy's getting rendered to the screen in a 2D situation. And here's some exposed properties from this object instance of this C# script. But if you right click here or just left click the sprite, it's going to reference an asset. And in this case, it's going to be an image. And here we see that we're in the project. We're in our file system, assets, characters, sprites, player idle.png. But notice this, that's not the same name. So if we scroll up, we see we're underneath something. And if I minimize it for right now, here's all our images in this folder. And if I click on one, we have what are called, this is the import settings for this asset, this file, and it's texture type sprite, 2D UI. That's great. It's not a texture applied onto a 3D material, onto a 3D mesh. But notice sprite mode, multiple. All right, so I want to find one that's single. Okay, Mr. Alien. Sprite mode, single. So there's not many parts underneath here, but you can open them up, and there's one sprite. It just happens to be the sprite is the exact same size as the file. So it looks like the file is 106 pixels by 260 3 pixels. So if I go show and explore, here's Mr. Alien, not his meta file, but just his photo. I was hoping that would show like the little wireframe. I don't know if I have Photoshop here. Let me see. See if it's still active. So texture image is just a 2D array of little squares, pixels. Each of them can have a color, RGB, usually 8 bits, or 2 to the 8 for red, green, and blue. 2 to the 8 is 256 choices. So you have a lot of reds, a lot of greens, a lot of blues. You make enough color variation to well represent the color spectrum to the human eye. And that's what this RGBA 8-bit, 4 channels. There's an alpha here. This is a PNG. So that's what these little checker things are. It's the invisible parts of the image, because everything's just rectangles and squares, and we have to know what we're not supposed to render to the camera. And maybe in Sprite Editor. Okay. I wanted to show you how like the image is broken up. But this is Unity's Sprite Editor. When you have a sprite that's a single mode, it's not too interesting. You do have your handles around here. Like this is the sprite that we're pulling from this image file. It just so happens the sprite is the entire size of it. But you could move this and say, okay, actually I don't want to render this whole thing. You know, he's really only supposed to look like this. But you know, in reality, he is supposed to be the whole image file for this situation, because this would just get cut off here. But you can see that there's borders and positions and stuff, and you can edit how you want your sprite to appear. And then when you're done, you click apply, or if you made mistakes, you click revert. I'm going to discard my changes because I was just messing with him. Yeah, I'm going to wait for Photoshop to open. But when we go to more a more normal situation in 2D games is you have what are called sprite sheets. So you throw in a whole bunch of images in one image file, and you make them in Photoshop or something. And then you chop them up in Unity, and we're going to play back the little sequences. So we're going to jump really quickly between all these different sprites, and it's going to make him look like he's alive. So notice we're in sprite mode multiple here. And I can go into the sprite editor, and he's all chopped up. So the good news is if you're making a sprite and you like purposefully chop up your image into something really regular, like 10 by 10 grid or 4 by 4 grid, however many sequences in your animation that you need, it's super easy to chop this up. It's like an automatic tool in Unity. You can just say, hey, automatically detect, and it's actually really smart, and it'll try to figure it out. Or you can say, hey, my sprite is in a 4x4 grid, and it'll chop it up for you. You could go through here, and here I just added a new sprite. So of the however many there are here, I just added a whole nother sprite to the thing. But I'm going to delete that and jump out, discard. Is Photoshop still not open?
So my question is like, why for Mr. Alien, like, why was it all colored and finished there, but for the player model, it's just a blank texture that gets put in engine.
So, well, Mr. Alien came in. So usually the process is you use a content creation package like a Photoshop or something, and you create the image, or you're in a 3D package and you create the model, and you bring it in, and then we set up the behavior in Unity. So like for example, the player is going to be swapping between these different sprites and playing. Oh, it's going to be swapping between different images and then running through the little sprites. But that's the same process as Mr. Alien. Like, it's still just an image.
Yeah, Yes, but I mean, like, if you go to the player, like, if you go to the player, if you go to the player model of the object, and scroll down to sprite render, you can change its color. You can move.
Oh,
I guess I'm curious how that works.
yeah, but Mr. Alien has a color overlay too.
Oh, it's an overlay. That's why.
Yeah, yeah. So we haven't gone into shaders and materials, but normally what's happened is you have a texture that connects up to your. See right here, we have this material sprite unlit default. We haven't gone into materials yet, but it's common to say plug this texture in and like render it to screen in whatever size and position that I tell you. And then there might also be like a color overlay because it's common to like duplicate it out, and if there's like many enemies you just kind of like change the little overlay color on. Yeah, so this is like a blending a color over your image. So for example, with the player, the only reason he looks blue actually is because he's tinted blue. He's actually white, or the artist made the sprites white, so you can tint them whatever color you want. In this case I tinted him like an orange. But yeah, the sprite render function's the same. You plug in a texture, an external asset, and you can do some other stuff. You can, if it's not flipped the right way, you can flip it. You could put a color overlay over it and some other stuff. But just to finish that conversation, Mr. Alien, I just want to keep zooming in, and then you see that this little pixel grid eventually appears. And so this is not real. It's not colored like this. This is a visual guide in Photoshop to kind of show you that we're now zoomed down to the level of the individual pixels of this image. So this image is something like 106 by 263, and each of these are just little colored dots. It's just when you zoom out enough, it looks all like nice, like smooth lines and blended colors and stuff. But when you zoom out far enough, it looks like nice resolution. But it's common for artists, they like when they're working, they'll like really zoom in and really work on stuff. And then for a user looks at it at a different resolution than the artist, and it's like looks real, looks lifelike to you. So player idle really has a lot of different images in it. They're just really small, but this one is 896 pixels by 756. It's a bigger canvas, and they just painted all these little characters on it. Usually, when you bring a texture into the game engine, usually you're dealing with powers of 2. So normally it's 16 by 16, 32 by 32, 64 by 64, 128 by 128. These are all powers of 2 are really nice and comfortable for a computer to work with. It doesn't necessarily have to be a square. It could be like a rectangle, like 128 by 256. But normally, you're working in powers of 2. And in this situation, this is almost a square. So I don't know why they just didn't make it just the basic square, but they didn't. All right, and so we're dealing with all 4 color channels and the blending. So while I actually had the color open, let me just talk quickly about that. So because I keep talking about color, but I didn't talk really about color theory a little bit. So this is the color wheel. This is a color variable down here. It's a property being exposed from a component object. And you have different little GUI widgets based on the type of property, type of variable it is. In this case, whenever it's a color, you can click on it and you can get this nice little window, this nice color wheel. So when I'm talking about color, when we talk about in computer graphics, we're talking about red, green, blue, and alpha. Usually it's 4 channels. Even something like JPEGs are something that doesn't have an alpha on it, where it's just red, green, blue. That's just 3 channels. So you have you're able to get smaller file size. So just know if you need like a PNG, usually for 4 channels to get your alpha in, or you don't need alpha. Usually you work with JPEG. Now in this case, I have some type of like orange selected, and in this range value here, we're dealing from values of 0 to 1. One you can think of like 100% all on. So our red is mostly all on. It's like 95% on. And green's about 68%, no blue, and all alpha. It's all opaque. So one way to represent colors in computer graphics is this like RGBA, but values 0 to 1, floats. And there's 4 floats, so that's a vector 4. We're going to deal with vectors quite a bit. So vector 2s are used a lot in screen space because you only need to know about X and Y, 2 floats, put them together into a vector 2 object. In 3D, you have X, Y, Z, so you have vector 3s. And in colors, it's very common to deal with vector 4s. And that A is there, even if usually it's like fully on. It means a fully opaque color. Now, there's other ways to represent color. When we do our code, though, we are probably just going to do like ranges of 0 to 1. But behind the scenes, the red, green, and blues actually ranges 0 to 255. So when we start counting in computer science, we actually start counting from 0. You'll see that a lot when we deal with collections or arrays. But we have 256 elements, representations, amounts of red, 256 for green and for blue. 256 is actually 2 to the 8. That's why we say it's 8-bit color. But you really don't enter numbers in like this. But you can see this type of representation. Hexadecimal is actually a decimal number. It's a different counting system. And this kind of is another way that you can represent different colors. We don't really use that. Hue, saturation, value is an interesting conversation to have. You don't really use it directly, but it's another way to represent a color besides RGB. Hue can be thought of as the aspect of the rainbow, the color that you're picking from. So notice as I move around this wheel, we're just moving the H, the hue value. And saturation can be thought of as how saturated a color is, like how washed out or how like full of pigment. So as I move the here left to right, it's how saturated is this hue, how saturated is this orange hue from washed out to fully vibrant. And value, as I move up and down, is kind of like how illuminated is it, how strongly lit up is this object. So we go to like fully lit up, full color, to all the way down into black. And alpha is just how opaque, from fully transparent to fully opaque. Normally values around here. Just pull down the saturation a little bit, pull down the hue a little bit, and you're pretty much safe to pick a color. That's like what are called like web safe colors. All right. So player idle. So this was imported in. It was set as a multiple sprite. Somebody went into the sprite editor and just said, hey, chop this up. And most of the time, if you just do an auto chop, like you do pretty good. Notice here, slice, type, automatic. Or you can manually set it up, like I want this many cells. Or you could actually sit there and just draw out the little rectangles, and you can actually name each sprite. But usually in automatic, and then you click slice, it'll attempt to chop it all up. And so now what we have are a sprite for each. And I can pull them out. These are like individual little sprites. And here's like all their detail information. And so when I open up player idle file, we have all these different sprites. And notice as I move through them, in the little preview at the right, it looks like he's animating. And that's all we do in 2D animation, is we just swap the images out super fast, and it looks like motion. Anything over like 15 frames per second changes in frame feels like motion to the human eye. Cool. So you can mess around with this. Could swap out different sprites, but I'm interested in how the animator is actually swapping out different sprites. The player is the most complicated part of one of these animated assets. So I'm going to just dive into the animator briefly because I just want to show you how all the parts are working. And then we'll get into it a little deeper. I don't know if I'm ready, and I can talk about materials and shaders right now. It'll be later. So let's take a look at this animator component. All right, and you can add components. They're down here. Everything's listed under 2D animation. We have some different type of sprite animations. But if I click on the controller here, we're going to go back into our project, and we're going to go down. It looks like it's under character and animations, and here's the player controller. So you need like one controller as a component object per game object. It's going to control all the different animations. And then we have all of the different animation files underneath it. So this means we got to look at two other windows. So here we have animation animator. All right, I'm going to open up animation animator. I'm going to open up animation. Usually animation I put at the bottom because it needs like a long space. And I'm just going to adjust my views a little bit. And I'm gonna move animator down here, and I want to click play, and I'm just gonna watch the animator in play mode. I want to see what's happening first. It's just that's probably killing my my screen recording. The volume's probably blasting out. There's a button here that someone showed me on Tuesday, so I'm gonna hit that. Yeah, it looks like you have to hit it while you're in play mode, but you could turn off the audio right here. Cool. So I'm gonna click on the player, and since I have the player game object selected, and the player game object has an animator component on it, we see what the animator is doing down here. So the animator is what's called a state machine, and that's a concept from computer science, and it's used a lot in animations and AI systems. It's like when you have very discrete states to move between, and there's a lot of like conditions that attempts to transition between them. And it's good to have like a visual node-based little graph system down there to see like, wait, what's happening? Where am I? Where am I moving to? So if I see here, we're in player idle, and if I open this up a little bit, we're in the player controller. I clicked here. This is a state in the animator, the controller. This state represents one animation. So the name of the state is player idle, and the motion, the animation file that's playing is called player idle. It's playing at a speed of 100%. And you can see the blue fill. It's like repeating the animation. Maybe if I zoom in, you can see that he's just playing the same animation over and over again. Now we have these lines going back and forth between different states, different nodes. These are transitions, and they have like rules placed on them. And if the condition in that rule ever becomes true, in this state, there's a certain amount of paths you can leave that state. And if any of those pathways, those transitions, if they ever become true, we'll leave. We'll go to another animation. So watch what happens when I press the arrow keys. Not only is the player game object, its transform, its position is moving in the game world, but his animation is changing. We're moving into that player run animation state, which is playing a player run animation. And so it looks like he's actually running. It looks like him, like his momentum is pushing him. In reality, as we'll see next, after we move off the animator and look at the code, his transform, the game object's transform is just moving left and right. And if I click on the player here, notice in the transform, the top right up here, the X value for left and right is just moving back and forth. So we're just doing that with the physics system because he happens to have a rigid body on him. But when you play an animation with it, it looks like he's actually moving. And if I press the space bar, notice the Y value in the transform is changing, going up and down. And you can see his velocity right here, X and Y, how quickly he's moving in these two directions. And you can, now that I'm jumping, you see this jump state is changing. We're keeping track of all this in the player controller. And when I jump, notice here the different animations. We're going from idle to jump to a land back to an idle. 2 different animations are playing. And so there's others too: hurt, death, spawn, victory. Looks like we're just going to focus over here for right now. And I'm just doing left and right and space bar to get these going. Cool. So player idle is referencing this animation file. So if I go into animation, I selected that animation file. This is what it looks like in the animation window. And if I click on the player, the play button becomes active. So I'm not clicking play in the animator. I'm not testing the game during its timeline. The game is not running. I'm in the animation window, and I have the game object clicked that has the animator controller on it, and I have one of the animations highlighted, activated in the animation window, and the play button in the animation window is available to me now. It's like I'm playing back my animations. I'm not in the game. I'm not worried about anything else. I want to know how this animation is playing on this player, on this character. And right now we're just looking at the idle. So it looks like the idle here starts at time 0, ends a little bit past 3 seconds. In fact, here are the frames that are playing back. And if I zoom out, there's potentially more time in the animation, but it's grayed out. We're not actively using that. So this is just the timeline, not of the main game. It's the timeline of just this one animation. And this is the name of the animation, and any other animations that are connected to this animator are showing. Notice it's all the player stuff. I can even go to run. And this is a half of a second animation. I can click play, and this is what run looks like. I want to go back. I was on idle, so let me go back there. Now, this shows all the properties that are being animated. So the way that the animation system works is usually an animator is controlling all the different animation states on one game object. And so the player has a player animation controller, and you can pick anything on the player game object, go into any of its components, and animate any of those properties, publicly exposed variables. So this one is just going to the sprite render. That's why it says player. That's the game object. Sprite. It's saying, hey, I'm going down into the sprite render, into the sprite property, and I'm changing it per time unit. So the way that when you animate sprites anyway, they give you like a little preview, and this is all like each little sprite changing. Like this is what it looks like per little frame. So a generic part of the animation window are these little diamonds, and these are called keyframes. So every time there's a keyframe, the game engine knows, oh, you want to change something. You want to change a property at that time. So I can scrub through the time. This little line is called the scrubber. And notice how I'm moving through the independent timeline of the animation. And this one happens to have a keyframe at each frame. So we talked about a frame previously in the update loop, in the update event, that the game engine breaks down time as small as it can into little fractions of a second, and it will run the update event. for every frame. And if there's no code, it doesn't do anything. It just runs. Boom, boom, boom. And if you have a bunch of code in the update methods of your game objects, it's going to have to, game engine's going to have to run through all those update methods of all these C# objects you've made, and it might slow down the game. But animation is part of this update event. And if this animation is supposed to be playing at that frame of a game, it will move through and play each frame of this animation timeline. And played back, this is what it'll look like. And it's really just changes, it's just playing different images of the sprite sheet. So if I go back to sprites, and player idle, it's just all these are being played back per frame in that animation timeline. You can animate anything else. In fact, in 3D, you'll see we're more going to animate the transform, the position, the rotation, the scaling. But for sprites, it's like changing graphics out, changing textures out. And so these are keyframes. And if I click on each one, if I pull this out, yeah, see here, we're at like this sprite, which is sprite 17. And if I keep clicking back, 13, 12, 10, 9. So we start at the first little square in that multiple sprite, and we're just moving 4, 5, 6, 7, 8, 9. So it's just swapping out a different image, a different sprite onto our sprite render, which gets rendered to the computer screen. All right, and same with all the other ones. Jump. In fact, notice jump. He's not actually going up. The animation is just him. He's just staying there. It's the actual moving the transform of the game object with the physics system that's going to make him look like he's jumping. And same with running. He's just running in place. It's just the animation frames are changing. Cool. So let's take a second. The last part I want to cover is piecing this all together with user input and the physics calls from the player controller. Let's pause for a second because I covered kind of quickly. I just wanted to like give you an overview of the sprite render and the animation. I actually am going to have to talk about in the animator these transitions. For example, idle to run. This arrow we're going from idle to run. The condition here is that velocity x must be greater than 0.001. So if I go over here in the animator to parameters, every animator has parameters. Think about as public properties. You can add them. In fact, there's a little plus sign here. You can add a float, an integer, a bool, or a trigger. A float's a decimal, and it's an integer. A bool is true or false, and a trigger is like a simplified bool. It like when you hit it, it executes whatever it's supposed to do, and it kind of resets. So instead of checking if something is true or false and doing something, you know that if this trigger is executed, you're just doing something. So there's different variables, different public properties you can expose out of the animator. And then you can set up your transitions between animation states. And when these properties change during runtime in the game, say, for example, velocity x, this gets before 0.01, they'll change. So let me see if I could just change this value here. Click play. Go into velocity X and put 1. No, you can't update because somebody's overriding it all the time. Okay, I can't. I want to show you I can tweak them, but some code is overriding them. The script, the player controller script is editing these. So once I get into here, I'll show you how it's like communicating with the controller. These are just sitting here. Somebody needs to go into the animator and tell them what their properties are. It's got to be one of your C# scripts. And I couldn't change that because somebody in an update loop is updating those values all the time. But before I go back to player controller, I kind of like touch the main parts of the player at a high level. Is there any questions or anything? Cool. So back in the player controller script. Here's the animator. Oh, it's internal. Okay. I was wondering why it's not a property sitting up there. So the player controller is grabbing the main things we're looking at right now is the sprite render and the animator on the awake. So it is aware of the other components and it's going to call stuff on them. So here's the update method. And basically it's gonna, there's too many rabbit holes to go through. I'm gonna just be careful how I'm glazing over stuff, but if control is enabled, so control enabled was like a bool up here, and it by default it's true, meaning the user can change the state of the player avatar. And some situations where this might be false is like when we're in that pause menu and you don't want the player moving around. But this is true, which means we're going to execute the code in that code block. This code block is designated here with these curly brackets. And we're not going to do this part, if, else. So if was false, we would execute the code in the else statement. But at runtime, this will be true. So what we're doing here is we're calling the input class. This is coming from the Unity engine, unityengine.input. And we're calling the getAccess method from that class. And you can pass in a string. So if you notice in the little comments, the notes, it's saying you can pass in a string called access name. And then it says it returns the value of the virtual access identified by access name. So, and we're passing in horizontal. So the reason that it's a little abstracted, but if I go to project settings and input manager and open up the accesses here, see there's like all this stuff, horizontal, vertical, file 1, 2, 3, jump, blah, 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 blah. The reason that they decided to set up user input like this is because that there's so many different ways users can interact with games. You have keyboard, you got mice, you got touchscreen for phones, you got game pads, you got hand tracking, you got whatever else. But there's some like standard conventions across all that. Usually there's a left and a right. Usually you're receiving input from somebody if they want to move a character to the left or right. So they have an axis called horizontal. And negative is to the left. When X value in the transform goes less, that's we're going to the left. And when the X value is increased, we're going to the right. So that's why left is mapped to negative and right to positive. And there's alternate buttons, so A and D. So it's very common for someone to hit the arrow keys or hit A and D, or maybe even on the numpad, you have like 4 and 6, or maybe on the gamepad, you actually have a little controller. So it's not always straightforward, like what you should be receiving in, which key you should be listening to, or mouse click, or whatever. So we have this nice input manager, and it's trying to abstract away a lot of the crazy details of handling user input for you. And in this case, we say, I want to receive the horizontal access from you, Unity, from your input manager. And if the player isn't touching anything, it's going to be 0. And if the player is touching the left or the A key or holding down the left controller, it'll be -1. And if the user's pressing down D or the right arrow or the right joystick or whatever, it's going to be 1. For keyboard and simple controls, it's only going to be like -1, the player's pressing left, 0, the player's pressing nothing, 1, the player's pressing to the right. For more advanced game controller, like haptic, I forgot the name they call it, where it's like very sensitive. But if you're just like slightly touching the directional controller, you're not fully pushing it to the left, you might get like -0.1, or that's how you get like really nice, soft, graceful. If you're like playing a driving game, or if you're just touching a little bit to the right, the player's just like walking, not running. But if you really push it to the right, the player will run. That's because it's going between mapping really small values from 0 to 1 or 0 to -1. But in our situation, we're using the keyboard. It's either you're standing still, you're going left, you're going right. 3 values. All right. So there's others too. There's vertical and fire and jump. We're about to also see. And if you see here, the jump axis is just mapped to the space button. Although you could set up your own stuff. So this line of code is basically saying, hey, Unity Engine, go tell me if the player is pressing anything on the horizontal axis. And we passed in a string into a method call that's sitting on the class called input, which is just a C# file sitting somewhere on the computer, and it gets loaded into memory. And you don't need to worry about that code. But this is going to, if you notice the method call here on the left, it says float. That's what it's returning. So this method call, methods are just functions owned by objects, and you just run, whenever you call a method, it just runs through the code that's sitting there in the method. But you pass in a parameter, in this case horizontal, a string that's called horizontal, and it'll do a check. It'll say, what did the developer want from me? Do you want the horizontal axis, the vertical axis, whatever? It'll do check, ifs or switch statements. And I'm saying, go check the horizontal. Saying at that update frame, that instant, that little fraction of a second, is the user pressing A, D, left, right, anything dealing with the horizontal? Let me know. And it's going to have a return statement. It's going to return back a value. In this case, a float, a decimal number. And we're going to throw that into move.x. So if I go up to move, up here, remember I said that at the top of our class, all this stuff, these are variables. And if they're public, we call them properties. And if they're private, we call them fields. But they're just little pieces of data. And move. So move is a Vector2. We have to declare our variables. We have to declare their types. A primitive means it's something really basic. It's already in the operating system of C#. It's an integer, a float, a boolean, a string. Anything more complicated is some object that we've defined. But they're all just objects. They're all classes, all objects coming from classes. So this is a Vector2 object. This is the type of the variable that we're defining. Vector2, you can see it as I hover over it, it's coming from Unity Engine. And Vector2s are super useful for screen space or 2D games. It's just saying there'll be 2 floats in there, and I'm going to do a lot of stuff to like help you out. You don't have to like get involved in the complex math of 2D, 3D, or 4D vector arithmetic. So there's just an X and a Y here. is the mover doing anything with the X on their computer? Anything with the Y? The Y would be jump values. Okay, so it's called move, and it was declared, but nothing was assigned to it. It's just default values, which is probably 0, 0. But the X property is going to be set every update frame to whatever the user is pressing. And so there's an X and a Y. The dot operator says, hey, this is an object. It's called move. It's of type vector2. And we're going to call something public on it. We're going to call a property or a method, something. We're going to use a dot operator to access something in that object. And it's in this situation, it's called a field or a property called X. It's just a little data value. It's actually of type float. So we're setting, if the user is pressing A, it's going to be set to -1, D to 1. If they're not pressing anything, it's going to be set to 0. And we're updating this every single frame. I'm going to skip this jump stuff right now because I'm getting late and I don't want to get into more rabbit hole stuff because it's already this the way that whoever wrote this, it's a little weird. So, or it's more complicated than I've already wanted. But just know that since this player controller is a child of, it's inheriting from kinematic object. Whoever wrote that class, you can call stuff from that class. So that's what this base is, saying, hey, go to my base class and go call its update method. This is a method call with the smooth brackets. So we have to go up to kinematic object, and we're going to call whatever's in this function. And basically it's saying target velocity is some field, some variable that's already here. It's of type vector2. We're going to set it to a default vector2 of 0, 0, 0. This is shorthand for writing x is 0, y is 0. And then we're going to call this method compute velocity. And if we go down to it, it's empty. So I think this code was not cleaned up or wasn't fully complete by the time they delivered this, but it's actually calling an empty method right here. And then what you have to see is there's a fixed update here. Let me just double check if there's not a fixed update over here. There's compute velocity here. Move, flip, flip, flip. Okay. Sorry, this is empty, but it's saying it's virtual. It's going to be overwritten by the child. So it's saying that we're going to call the code that's over here in player controller. So we're back over here. There's a bunch of jump stuff. I'm going to ignore it. What I really want to get to is here. So this is called every update loop or reading in user input. Yeah, it was a little annoying. We're jumping to method, but ultimately we get here. So this is saying if move.x is greater than 0.01, remember I said the gamepad controllers can read like really discrete values. So this is checking if we're using like keyboard or really nice gamepads. If we're not on 0, and if we're in a little bit in the positive, meaning the user is moving to the right, then sprite render.flipx equals false. So if I come over here, remember I was showing you in sprite render, you have this flip. So it's like we're flipping the render. Be like, if he's moving to the right, he should be going that way. If he's moving to the left, we should flip him and make him look like he's moving to the left. Else, if movex is less than 0.01, meaning it's not 0 and it's not positive, we should flip it because we're going to be moving to the left. And we're checking this every update frame. Now we're going to our animator. Remember those parameters I was showing you in that animator. set bool. So we're going to set a bool on the animator called grounded to is grounded. That has to deal with jumping. So I'm going to skip that for now, but set float. Set the velocity x float on the animator to this. So take velocity x, which is being calculated here. I'll get there in a second. And divide it by max speed. So there's only some max we can go. Let's just say we can only go 10 meters per second or whatever. Let's just say we're currently going 1. That means we're going 1/10 of our max speed. And that's what we're passing into our animator. And we're absolute valuing it. So whether we're running to the right or running to the left, it's just a positive number when it comes into the animator. And that's this velocity x right here. That's why I couldn't change this, because every update frame is being updated by our code. But if you look at this transition here, whenever we're idle, and velocity x gets greater than a really small number, we're going to transition to our running animation. And whenever we're in running, if I click on this this transition back to idle, whenever velocity x gets less than that really small number, whenever it's basically getting to 0, we're going to leave our running animation and go back into our idle animation. Okay, so here we're setting that, what they're calling a parameter on the animator, that little property. And that's what's allowing us to know if we should be in our idle animation or our running animation, because I'm just looking at those two animation states. Okay. So another last little piece of the puzzle of how this character is moving on screen. That was how the animation is changing. But how is the transform? How is the character actually moving around? So if I click on the player there, this position X, how do we move this left and right in our game world? So it's actually over here in this fixed update and kinematic object in the base class called kinematic object. There's fixed update. And just make sure there's nothing in player controller. Okay, we seem pretty safe. So remember, there was update. We run it as quickly as we can. It's kind of a variable amount of time. It's just how good is your computer, how much code are you running. And then there's late update. Is like if you ever need to run anything after all the update is done for that frame. Then there's fixed update, which deals with physics. And it's fixed time steps. It's very regular in how often it's called. I think it's 0.02 seconds. And that's, we do our physics calculations in there because that gives us a little regular time units. So this is doing some Y checks if we're falling. I'm not going to worry about that. Here, our target velocity dot x is equal to our velocity x. So here, all the way at the end here, this target velocity ultimately grabs move times max speed. So move is a vector 2, x and y, and it's just, we're just figuring out user input with that. And in this situation, we're really only thinking about the x. But when you say move times max speed is some property up here set to 7, I think. But I think I was messing with this last class. We changed it to 3 when we were in the inspector. So it's really 3. So it's whatever this move value is. So if you remember, it's for us, it's just -1 if it's left. It's the x property we're really interested in. -1 if it's left, 0 if we're standing still, and 1 if it's right. And we're just multiplying it by 3. Because somebody was tweaking this, and found that that felt right. Anyway, that's what's happening here, and it's getting thrown into this target velocity, which that's what this is. And so we're grabbing this x from it. Let me skip all this until I see where perform move. Okay, this I'm not getting into casting why we're doing that right now. Okay, we're not worrying about if we're jumping, if we're landing. Here, if we're grounded. Cool. So it's doing a bunch of calculations, and right here at the bottom, it's taking the position of a rigid body. I'm not diving into the physics system to any extent right now, but ultimately, it's taking the rigid body component of our game object, and it's saying, hey, I want to update your position, your X, Y, Z, your position in the game world. Whatever you're currently at, I want you to add our move value. There's some additional math going on here. It's being normalized, and there's a distance. But after all that calculation, I'm figuring out there's some number. Remember, it was like -1 or 1 times 3, and then there's a bunch of stuff happening here that we're going to have to step through, but I'm not going to step through it right now. But that 3 is multiplied or done some other stuff, and some distance is calculated, and we're adding it to our position. So the position of this rigid body right here, this physics component that makes it like an active entity in the physics system, we're just updating its position, and it's controlling this here, this final, like our position on the transform. So this is, it's always going to get hairy when you're dealing with the movement of players, and you have to read in user input, and you have to do a bunch of checks, like what's happening, are they jumping, are they touching an enemy, whatever. But ultimately, you come down to saying, okay, update the position. Or you might do it a little differently. You might say, oh, update the velocity or the acceleration of the rigid body, and it will do its math for you, and it will figure out what its final position is. In this case, we're just saying, tell the rigid body its new position is this. And just like it adds a little bit to the X if the player is holding right, it removes a little bit from its current X position. So maybe I'm just going to put a little print statement here, and we'll debug out the body position all the way at the end. Let's see, it's a vector 2. Usually there's like a 2 string. I'll just explain that in a second. Let me just see if it works. Then I kind of did the whole roller coaster from render to animator to user input to physics. And that was a big explanation of a big part of this game here. And then I'll leave it alone at that. Go to the console because I'm printing something out. All right, this is my little print message that debug.log. And all the way at the end, saying like, what is this position? What is this position of this rigid body component that's on this player game object? And notice it's printing this value, and look up here what our ending position is. They're almost identical. I think this one's just truncated a little bit. It's just cut off.
What about the values above it?
Those are older statements. No, it's older because this is a newer one, but I'm trying to figure out why the values.
Could it be for the different components in the rigid body?
Oh no, because it's the enemy. So the kinematic object is inherited by the player and the enemies, so it's like everyone is printing out. But as I move them a little bit, look that these values get reflected, and up here in the transform, that's what the values are. So this is like the hairiest part of this game project. I kind of tried to move through without getting stuck in too many foreign concepts to you. But in a nutshell, um, we pull in user input in the update loop. We always checking, is the user doing anything? Is the user doing anything? And then we have to do some computation. And part of that computation is, hey, if the user is trying to move to the right, we got to set up our renderer to be positioned that way. If the user is trying to move to the left, we flip the renderer that way. We got to tell our animator what's happening, because the animator needs to decide what different animation states we should be in. And then we just call this, we tell this variable target velocity, here's the new information. Here's what the user did for that frame. And then the parent class to everything that moves to the player, to the enemy, is kind of taking over from here. So here we just kind of updated that target velocity. And then this fixed update is called every fixed little section of time so that we can do our physics work. And there's all this crazy stuff going on in here. And I don't want to go deep into physics code. This sort of it's too crazy this early in a class. But ultimately, it's like figuring out if he's standing on the ground, if he's jumping, if he's hitting an enemy. We should adjust how much of a push, in this case, left and right. We're just talking about moving left and right. And after all this, we just update our rigid body. Like, hey, wherever you currently are, whatever your X and Y was, because we're doing a 2D game, add this amount of more to it. You know, if it's some left, add more to the X, or remove some of the X, go left, right. If you're jumping and gravity is pulling you down, we're going to lower the Y, or if you're just jumping, we're going to have you go up, but we're not looking at jumping right now. We're just seeing how the X value gets impacted. And then I just debugged it out. But when you debug, when you print something out, ultimately it needs to be a string. But look, I'm printing out a vector2 object. So every object has like this toString method saying, hey, whatever you are, there must be some little method on you that says, how do you make a nice little string from you? Some developer figured it out. So you call it toString method. And that's what's being printed out to the console. All right. Yeah.
Can you explain vector 2?
Yeah. So in the game world, you're going to deal with vector 2s, vector 3s, and vector 4s. And really what they are is just either 2 floats or 3 floats or 4 floats. And let me see Unity's. So this is the scripting documentation for Unity. Super useful. Unity's been around for a really long time. So if you ever run into any issue, just like it's all about how you pose your question in Google. But chances are somebody's talked about it already. Stack Overflow is a great forum. Everybody's talked about everything about game development, web development, or whatever, but game development with Unity. And so there's a lot of answers online. So one of your resources is going to be the scripting documentation. And everything about Unity's API or libraries are in here. And there's a lot of additional information too. But a vector 2, think of vectors as like a composite of floats. When you add a float together, like 2 plus 4, it's easy for us to understand it. Oh, that's 6. You can even do 2 plus 4. Like add this float plus this float in your programming. It's pretty straightforward. But when you're handling vector 2, 3s, or 4s, it gets kind of annoying when you add a vector 2 to a vector 2, you actually have to add them component-wise. So you add the x's, you add the y's, you get a new vector 2. And for vector 3, you have to add all 3 plus 3. And for vector 4s, which we use for colors and rotations, it gets even crazier. And then there's other math functions like dot products and cross products and like normalizing stuff and I'm not going to get into all this right now, but it's even more complicated math. It's like you don't want to do it. So if you use an object, you can call methods and it like does the math for you. So vector 2s are used a lot in screen space and 2D games where you only have to think about the x and the y. And it's really, you can just call these x and y properties on them. And if it's a vector 3, there's going to be a z property. And it's like pulling out the one float. It's a nesting of floats, but you just want to pull out the x. So we use vector 2s for user input because we want to know, are they trying to move the character left and right? Are they trying to move the character in a jumping fashion, press the space bar? But basically it's just like your graph coordinates. It's like wrapping this idea up into one object. So you don't have to like separate. You don't need to keep track of like 2 float variables and do whatever you got to do. Then you just wrap it up in a nice object and have somebody else handle the details for you. Yeah. And later, I mean, I'm gonna have to approach some topics of especially when we get into 3D. Like you have to understand a little bit about how to use the vectors to know like what's happening in the game world. It gets a little dicey, so we'll just be light with it. But when we're here in 2 vector world, like we did hit this idea of normalizing the vector. So no, not the normal. So it's common to use vectors for understanding like directions and orientation, especially how different, like say you want to know if the enemy is kind of facing the player, you look at like what direction they are in the game world. That's how you know like, oh, the enemy is close enough to the player and it's looking at the player. The enemy should try to attack. So it's common to use vectors a lot to understand like where stuff is and where they're pointing at each other. But toward the end of the code I was looking at, they did a normalize. And I don't want to talk about the normal. I want to talk about normalizing. Yeah, this might. I don't want any math right now. Just say that. Vectors can be like oriented anywhere around like your coordinate space. So if it's just a vector of 1, 0, meaning an x of 1 and a y of 0, you're going to be just like pointing to the right. You're not going to be pointing up or down at all. But there's situation. This is like a vector where it's pointing 3 units to the right and 4 units up. So that would be a vector 2 of 3, 4. So if you said your vector 2 object dot x, get me my x float, it's going to return a 3. And if you did dot y, it would return this 4. So a vector of 3, 4 means it's pointing this way in our game world, a little bit higher than horizontal, a little bit more vertical than horizontal. And this is good to have like this absolute vector. Like say if I'm holding down the A key and I'm jumping and we do our calculations and we figure out, oh, okay, in the next frame, the player object needs to move 3 units to the right, 4 units up from where it currently is based on all the user input. And so we have this vector 2 of 3, 4. And say if the player was here, next frame he's going to have to be up here. Sometimes it's useful to normalize a vector. So just to express the direction of the vector, but don't give it a magnitude. Don't give it a quantity, how big it should be moving or pointing. So when you normalize a vector, you get it to the size where it's of size 1. It's a unit size. So the line is 1 unit, whatever your measurement is. So if you add up the x and the y, if you do like that distance formula where it's like x squared plus y squared square root, like what's the total size of that vector, it'll equal 1. So here, this is 3 squared plus 4 squared. So this is some, and take the square root of that. That's not a size of 1. It's like kind of big. So this tells us something interesting in the math that we're doing, but sometimes you just want that direction but size of 1. That's why this is less than 1, this is less than 1. If you do your distance, this will be 1. But it's the same orientation. Vectors are hard to deal with if it's new for you, but they get easier the more that you use them. And in games, they're like, oh, everything is just like coordinate systems. Is x, y's. How much is everything moving each frame? And so we use vectors like all over the place for that. So we're not going to get too heavy into the math behind all this, and I'm trying to like hide a little bit from like this is kind of, I know this is very scary code, but we're like in the deepest part of the deepest part in physics. You can get a little scary look at, like, here's a dot product here. I'm not even explaining what this stuff is. I just kind of glazed over. But we'll dig into it, and I don't expect you to like understand how to write the code. It's just understanding the concepts and how they're used, so that when you start thinking as a game programmer, you can start to use it. You can understand what's happening. But yeah, there's gonna be a lot of vectors. It's the essence of it. But I'm starting 2D instead of 3D. It's because 3D gets, the need is greater and it's more complicated. But we're not programming the games. We're just like breaking stuff down so you understand what's happening. Like, you understand the concepts. I'm not going to give you math problems. I'm just going to understand, like, do you understand what the point of these vectors are and how they're being used in the game engine? All right. Anything else? Cool. We're done for today.